Welcome to Module 7b from our series on artificial intelligence. The topic of this module is advanced or more advanced PyTorch for image recognition. It will teach us to build a machine learning based image recognition algorithm from scratch via PyTorch. I'd like to begin by asking a question, and that is, can we implement this machine learning example, the one from the previous module, where we want to recognize handwritten digits 0 through 9? Can we do this with fewer than 500 lines of PyTorch code? And the answer is yes, at least for the primary executable script. There are some secondary questions that I'd also like to introduce. The first being, how do we optimally design and structure machine learning software for image recognition in terms of maximizing performance as well as scalability? The second question being, in general, how do we implement more advanced PyTorch-based machine learning projects, more advanced as compared to the perceptron from module number 6? Third question being, how do different loss functions and optimizers affect machine learning performance? Fourth being, what role does the learning rate, momentum and dampening, as well as weight decay play in machine learning and the success rate of that machine learning algorithm? And then fifth, what is an adaptive learning rate? The focus of this module is explaining Python and PyTorch code. As such, I provide 3 ways that you can download this source code. The first is Google Colab, which is probably the easiest way to access the code. Unfortunately, however, this version doesn't allow you to add new training images nor change the 4x4 sensor grid that we presented in the previous module. You can also access the code from GitHub or my personal Dropbox. For most of this module, we're going to be focusing on the version that is available in the Dropbox. Before we discuss the project structure or the code itself, I did want to take a minute to discuss Google Colab. You can see that I've loaded the Google Colab notebook for this project on my Mac. It's pretty easy to navigate. We can click on the folder icon as well as the content tab, and this shows us all of the files that are available for use by our Python script. Right now, we're missing several important files. In order to rectify that, we can go to the first script, the one that's labeled step number 1, click on the play button. And if we scroll down, we'll see messages telling us that those necessary files are being loaded into the content folder, and we can also see them being brought up over here to the left. So what are these files? The first is the image processing library that we've discussed on several occasions. The other 2 are data files. Now, it would be pretty difficult for us to download hundreds of training images from Google Drive and upload them to the Google Colab content folder. As such, what we've done is use another PC to process those images, vectorize them, and yield the arrays that serve as inputs to the neural network. And this is the reason why when we employ the Google Colab version of this code, we're unable to change the resolution of the 4x4 sensor grid. Once these files are loaded, we can scroll down to the second script, the main script, hit the play button, wait for 1 second here, scroll down a little bit more, and then see the results of our machine learning. You can see here these numbers, 7,500. This is telling us the iteration number. It's telling us error, the optimization method being employed. And if we scroll down to the bottom, we can see the results. And for this specific run, we get an accuracy of approximately 90%. Now, I don't want to jump into this right now because we will discuss these results at the end of the module. I did want to spend 1 second talking about the project structure, which unfortunately can be a little bit confusing, a little bit convoluted. The main directory is called .venv. It stores a self-contained Python virtual environment. It includes its own interpreter and libraries and isolates dependencies from system-wide Python installations. Now, this may be advantageous for many of you that are working on multiple Python projects at the same time. It prevents changes associated with one project from affecting the others. Now, I do know that this project structure, at least the way that I've implemented, is suboptimal, and this is something that I do plan to correct for future modules. Now, within that main directory, we have 4 subdirectories. One is called include. This directory contains header files required for compiling Python packages with their native extensions. We have the library subdirectory, and this contains the standard library modules and all third-party packages installed in our environment. We have the my scripts subdirectory, which essentially contains all the Python code that I generated. It has 2 scripts of interest. One is the image processing library, the same one that we discussed at length in the last module, module 7a. And then the other is the main executable script, which actually performs the machine learning. The 4th folder is called sample images, and as the name suggests, it holds all of the training and test images. Finally, we have the requirements.txt file, and this lists all necessary Python packages and their versions. So what you can do is run the Python package installer, essentially pip install -r requirements.txt, and this reproduces the development environment on your PC. Now that we understand the project structure as well as how to access the code, let's review it section by section as well as line by line within those individual sections. The nice thing about this is I'll largely be reading from my own comments within the code, and that's something you can do on your own as well. I did want to reiterate that we are focusing on the Dropbox version of the code, not the Google Colab, and what that means is that this code does have access to the training images and does allow us to manipulate the sensing resolution. So let's start in the top left-hand corner. First, we need to import the necessary libraries. I don't think there's much to say there. We then move on to defining some important constants. One, or actually two of those, are the minimum and maximum learning rate. You may be asking why there's a minimum and a maximum, not just a single value, and that's something that we'll discuss when we get to adaptive learning later on in this module. We then define the number of horizontal as well as vertical divisions within our sensing matrix. We're using the same values from the previous module 7a, so we'll have a 4x4 sensing matrix. Moving on, we need to define the number of sensors, which will simply be the number of horizontal divisions times the number of vertical, so we'll have 16 again. This number is important because it tells us how many inputs our neural network needs to accept, and it's obviously an important value in defining that architecture. The length of the training vector, right, this defines the number of values associated with a given training sample, or the number of columns associated with a single row of our training matrix. Now we need 16 values corresponding to the 16 input values, as well as one additional, which represents the ideal label. So if the sample corresponds to a handwritten number 6, then we need a label indicating to the algorithm, to the supervised learning algorithm, that it's a number 6. We then define the number of outputs, which should be the same as the number of categories, the number of classifications. Since we're trying to recognize digits 0 through 9, we have 10 classifications or 10 categories. In purple, we define the number of previous iterations to be checked for convergence. We've talked about this before. We never want to make a judgment regarding convergence from the error or loss yielded by a single iteration or yielded by a single training sample, because by luck, those synapse weights could accurately represent the behavior reflected by any individual training sample. What we do want to do is examine a window of values, in this case perhaps the last 100 error or loss values yielded, and then employ the average loss or the maximum loss in order to judge whether convergence has been achieved. Here we define the convergence parameters. What is the maximum loss or maximum error for convergence? If we were to increase that value, we would be loosening the convergence requirement, and if we were to lower it, we would be tightening that requirement. And then finally, we define the maximum number of iterations that we allow the loop to run before breaking it. Now that we've imported any necessary libraries and defined any relevant constants, we can move on to loading our training and test data. Now note that this portion of the project is not relevant to the Google Colab version because it doesn't have that capability, nor does it have access to the training or test images. This section doesn't involve any machine learning specific tasks, and as such, we're not going to review it in the same level of depth as others, meaning that we're not going to go through it line by line. The function of this section is to load the training and test images from the sample images directory, as well as generate the training data and test data tensors. Remember, these are the same .pt data files that we downloaded from my Google Drive and uploaded to the content folder within the Google Colab notebook. Note that even the Dropbox version of this code loads the training and test images only if the corresponding .pt data files were not previously saved or are not present within the project directory. What that means is if you want to change the sensor resolution, or if you want to add, subtract, change the training samples, and you want to reload and redefine that .pt data file, you'll have to manually go into the project directory and delete them. Now, both of these data files, both tensors, are structured similarly. The first column contains the ideal output label, and the remaining columns in this case would be 16, but it could be more or less if you change the sensor resolution. So those remaining columns define the sensor-derived inputs. Now we move on to a more interesting part of this project where we define the neural network model. We've named it Neural Network for Image Recognition. It's defined as a subclass of the torch.nn.module class from the PyTorch library. You may remember we used a similar structure in module number 6 for the perceptron example. This class has two parts, or two methods, one being the constructor and another being a forward propagation method, but we're going to discuss that on the next slide. Now, the constructor method obviously will initialize the model's structure. It allows us to perform several tasks. One is to define the number of inputs and outputs. So here we define the number of inputs. Here we define the number of outputs. We could define this as 16, define this as 10. We use the command highlighted in yellow in order to enable class inheritance. And then next, we need to define the layers, the actual structure of our neural network. In module 7a, we decided to employ a shallow neural network structure with two layers, one hidden layer and an output layer. 1, and 2. The hidden layer should accept 16 inputs and generate 32 outputs. The output layer should accept 32 inputs and define 10 outputs. Both the hidden and the output layer are defined as instances of the torch.nn.linear class from the PyTorch library. Here we define the number of inputs for the hidden layer, number of outputs for the hidden layer. Again, we use the linear class. We define the number of inputs for the output layer and number of outputs for the output layer. Finally, within the constructor method, we need to define the activation functions, the rectified linear unit, as well as the sigmoid, and both of those are just defined as instances from their corresponding classes within the PyTorch library. Next, we discuss the second method within our model. The forward method defines how an input, which we call tensor input x, flows or propagates through our neural network. In order to understand or define how our neural network behaves, we need to in turn define the behavior of those individual layers. Now, we already said previously that this neural network is composed of 2 layers, a single hidden layer as well as an output layer. And we already know how a neural network operates. Each neuron within a given layer accepts a set of inputs, which we're calling x. It has some set of synapse weights associated with it. It applies a weighted sum to those, and then an activation function to that weighted sum in order to generate an output. And so we can see that similar behavior reflected down here in the code. We have our hidden layer. It accepts the same tensor input x supplied to the forward function, and it applies a weighted sum using the self.hiddenLayer object defined within the constructor. Note that the synapse weights are automatically defined by the PyTorch library. We then apply an activation function, in this case a rectified linear unit activation function, to the weighted sum, and that generates the intermediate output y1, which we would expect to have 32 values within it. That is then provided to the output layer. We can see tensor y1 right there. We again use self.outputLayer in order to apply the weighted sum, and we apply a sigmoid activation function to that weighted sum, generating an output tensor out y2, and then we return that output to the parent, wherever that is within the project. So let's revisit the neural network model defined by the previous module for this example problem for recognition of handwritten digits 0 through 9, and let's compare it to the PyTorch code from the previous slide. And what we'll see is that PyTorch doesn't play a major role in loading the training images, image processing, or vectorization. In fact, PyTorch is predominantly concerned with the right-hand side of this figure, the actual neural network structure. Now, quickly reviewing that structure, we see it's a shallow neural network, again, with 2 layers. In the red, we have the hidden layer, which employs 32 neurons and rectified linear unit activation functions. We have an output layer shown in gold with 10 neurons, each of which employing a sigmoid activation function. And so what we see is that we're able to build this network using classes from the PyTorch library. The torch.nn.module class defines the model in its entirety, the neural network in its entirety. It essentially defines the canvas on which we draw or create our neural network. Now we have 2 layers. Each one of those layers is defined by the torch.nn.linear class. So we have defined within our model self.hiddenLayer and self.outputLayer, and both of those are defined in terms of the torch.nn.linear class. Now the activation functions, which I guess are located inside of those neurons, are defined by 2 different classes. For the hidden layer, it would be torch.nn.rectifiedLinearUnit, and for the output layer, we would be using torch.nn.sigmoid. Now that we've imported any necessary libraries, defined any appropriate parameters, we've loaded training images, and we've defined our neural network model, we can move on to configuring, initializing, and instantiating that neural network. Now, if you've downloaded the code and you're following along, hopefully that should be pretty easy to do. Really, we started at the top of the script and we're working our way downward. So the first part of this section of the code requires us to call our neural network model. And that's essentially what we've done here. Right? We've created an instance of our neural network for image recognition, which we defined on the previous slide, and we call that instance myModel. We define the number of inputs that it accepts, as well as the number of outputs that it generates. Next, we need to define our loss function. We are going to employ a mean squared error loss function, and this is pretty easy to do. We create an instance of the torch.nn.mse loss class from PyTorch, and we call that myLoss function. Next, we need to configure the optimizer to perform stochastic gradient descent. Pretty straightforward again. You can see the command shown here in purple. We create an instance of the torch.optim.sgd class from PyTorch. Again, this sgd is telling PyTorch that we intend to use the stochastic gradient descent optimizer. We call this instance myOptimizer. Now, what parameters or inputs do we feed to this class? We need to feed the model that it will be optimizing, more specifically the parameters of that model, which in this case would be the synapse weights. We also need to feed it several other parameters, such as the learning rate, the momentum, and the weight decay. Now, we should be familiar with what a learning rate is. If you're not familiar with momentum or weight decay, don't worry, we're going to discuss that in this module specifically. Finally, we need to initialize loss tracking, or an array to track our losses. Essentially, this array stores the loss or error values generated by the previous 100 or so iterations of the machine learning algorithm, and then what we're going to do is look at the maximum from that array in order to judge whether convergence has been achieved. Next, we define the iterative part of our supervised learning algorithm. We begin with the training loop. We employ a basic Python for loop with k epoch as our iterative variable. It tells us which iteration we're performing, and that loop continues until we reach convergence and a break statement is called, or until we reach this maximum value we defined earlier. Within the loop, the first thing that we do is reset the gradients, right? We zero out the gradients within the optimizer to prevent accumulation of values, which has negative side effects. After that, we select a random sample from the training data set. We know that for supervised learning, for each iteration, we need to choose one sample from the training data set to provide inputs as well as a ideal labeled output. One way to do this is to start at the beginning of the training data set and progress one by one till the end, and then start over. This is suboptimal, however, because it does introduce some bias to our training process. A better way is to choose one sample randomly from the data set, and that's what we do here. K-train is the index associated with that randomly chosen sample. After that, we need to extract the inputs and outputs associated with K-train. So we have x train k. This is a 16 by 1 array that contains the inputs generated by the sensor matrix associated with this index here. Then we have correct category shown in purple. This is a single numerical value taken from the first column of the training data matrix, and it essentially tells us what the ideal label is for the sample. If it's a 6, that value would be a 6. Next, we define yidealk. This is a 10 by 1 array that merely expands the correct category value. We have two examples here. Let's say the correct category is 3, then our yidealk would have all zeros except for value 3. So 0, 1, 2, 3. If our correct category is an 8, then this array will contain all zeros except for 0, 1, 2, 3, 4, 5, 6, 7, 8. Is a number 1. Now we do this because we want the format of our ideal output to match the format of the predicted or the calculated output. After that, we must calculate that model output or generate the predicted output. For that, we take our inputs and we supply it to the model we defined previously. Now, if we want to, we can explicitly tell Python that we're calling the forward propagation method. However, if we don't define any method there, PyTorch will assume that it's forward propagation. This generates the calculated or predicted output with a format similar to this array. Finally, on this slide, we calculate the loss. We already defined an instance of our loss function, of our mean squared error loss function, which we call my loss function. So we take our calculated output as well as our ideal output, which should have the same format, supply them to the loss function, and that generates the error or the loss value. Next, we check for convergence and update our synapse weights. Note that the code presented by this slide is still contained within the same for loop from the previous. The first thing that we do is implement an adaptive learning rate. Now, we haven't talked about this yet. We will at the end of this module. To provide a preview, this entails us updating the alpha value from iteration to iteration optimally. Next, we store the most recently calculated loss or error value to this array loss. So over here we have loss k.item. This is that loss value we just calculated, and we store it to this array. After that, we check for convergence, and this is pretty straightforward. If the maximum loss calculated over the last 100 iterations or so is less than the maximum allowed loss for convergence, then we have achieved convergence. We can break our loop and skip these next few steps. If not, then we have to continue with the update. That involves us performing back propagation and computing the gradient of the current loss tensor with respect to the graph leaves or with respect to the synapse weights. After that, the optimizer will employ that gradient to step the process forward or to update the synapse weights optimally. This is the end of the loop, and we have to return to the beginning, but hopefully with synapse weights that are slightly more optimal for this upcoming iteration as compared to the previous. Once our model is trained, we can test it. We begin by looping through all the samples within the test data set. We use a basic Python loop with kTestSample as our iterative variable. That tells us which sample we're currently looking at. Note that the test data set should not be the same as the training data set, right? If we use the training data set for testing, that can mask an overfit model. Next, we extract the inputs and ideal output or ideal label associated with kTestSample. Xtest will be a 16 by 1 array, assuming our 4 by 4 sensor grid. It'll be a 16 by 1 array containing the inputs as generated by that sensor grid associated with kTestSample. Y true will store a single numerical value, which represents the ideal classification or ideal label, again, associated with that sample. Once we have our ideal output, we need to use our trained model to generate hopefully a very good prediction of the classification output. We use the command over here. Again, we're going to call our model, supply to it the inputs associated with our current sample. Now, PyTorch will assume that we want to perform a forward propagation. However, we can also write that explicitly to tell Python to do so. And this generates our Y predicted array. Now note that this array contains 10 independent probability values, one for each potential classification. And what that means is you could have a 40% chance that the digit is a 0. You could have a 22% chance that the digit is a 1. You could have a 5% chance that the digit is a 2, and so on. There's no guarantee that there will be a clear winner. As such, we use the code in green to convert this array to a single prediction, and we do so in 2 steps. First, we find the index of the value from this array with the maximum probability. Then, if that maximum probability is greater than a minimum threshold of 50%, we save that as the predicted class. If none of the probabilities are greater than 50%, then we'll return an inconclusive result. And finally, we need to calculate the accuracy as the percentage of the predicted and ideal or true classifications that match one another. Next, let's revisit the results generated by our machine learning algorithm. We see that this version is running in the Google Colab environment. There's 3 values that I'd like to highlight: this matrix, a second matrix of similar size, and this numerical value. The first matrix contains the ideal classifications associated with each of the test data samples. The second matrix contains the predicted classifications yielded by our trained model associated with each of the test data samples. One would expect the number of elements in this matrix and this matrix to match. Third, we have the accuracy, which in this case is 95%, meaning we expect a 95% match between the values of this matrix and this matrix. Now that we have a working machine learning algorithm for 0 through 9 digit recognition or image recognition, I want to ask a follow-up question, and that is, what tools and methods did we use to optimize training performance? Now, this module only begins to answer that question. Later modules, such as the next, which will most likely be on the topic of gradient descent, will dive into that topic further and provide some mathematical justification. In response to that question, I'd like to discuss 3 topics: adaptive learning rates, momentum, and weight decay, all of which we at least mentioned earlier on in this module. We already know that the learning rate, represented by alpha, quantifies the effect of each training iteration on the synapse weights. This table compares the advantages and disadvantages of larger versus smaller learning rates. As far as the advantages of a larger learning rate, it can yield faster convergence, it can allow our algorithm to escape the region of attraction of shallow local minima, and it can result in fewer iterations being required for convergence. The advantages of a smaller learning rate: it can result in a more stable convergence characteristic, it can yield a solution with higher accuracy and precision, and it can yield an algorithm that's better at dealing with noisy gradients and noisy data. With regard to the cons or disadvantages of a larger learning rate, and obviously these 2 boxes mirror one another, those disadvantages are: a larger learning rate may result in our algorithm overshooting a minimum, it may yield a less stable or divergent series of updates, and it may result in lower solution accuracy overall. With regard to the disadvantages of a smaller learning rate, it can result in relatively slower training, it may return a local minimum instead of the global that we desire, and it may result in inefficient use of our computing hardware. Larger learning rates are best used for early attempts at training, when we're looking for the region of attraction associated with a global minimum. Smaller learning rates are best used for later attempts, when we already understand what initial conditions fall within the region of attraction for that global minimum that we desire, and we can use it to simply fine-tune parameters and maximize precision. An adaptive learning rate adjusts the alpha value during training based on gradient behavior to emphasize the pros, the advantages of both smaller and larger learning rates. This figure compares the behavior of a gradient descent algorithm for larger versus smaller learning rates. For both plots, the x-axis represents the input. I'll use x for that. The y-axis represents the value yielded by the objective function that we want to minimize. Both plots show two local minima, as well as a single global minimum. We know that the ultimate ideal objective of our gradient descent algorithm is to reach this point, the global minimum. Both algorithms start with the same initial condition. With a smaller learning rate, the gradient descent algorithm takes smaller steps, and as such is able to hug the side of this slope. Unfortunately, that leads to the smaller learning rate returning this local minimum right here. The algorithm is not able to climb that hill. It's a gradient descent algorithm. It's not able to ascend the hill. With a larger learning rate, the gradient descent algorithm takes much larger steps, which, as we can see, may lead to unstable and divergent behavior. It also, unfortunately, may lead to the gradient descent algorithm skipping over the minima that we are interested in. Let's discuss one potential implementation of an adaptive learning rate, specifically the one from the Python code referenced in this module. Now, we employ a relatively simple adaptive learning rate strategy, one that observes the effect of an update on error or loss. And there's two cases that we need to discuss. The first is that the update associated with an iteration reduces error or loss, and this is generally considered to be good. If that's the case, then we increase the learning rate. Why not take bigger steps if we're pretty sure that we're headed in the right direction? The second case is if the update associated with an iteration increases error or loss, which is generally less desirable, then we decrease the learning rate. Bigger steps may skip over important features when we approach the global minimum, and this could signal that our algorithm is entering a highly nonlinear region with steep changes in gradients. Now, in order to understand this approach, we need to take a look at the graphs to the right. We begin with the top one. On the x-axis, we have the iteration number. On the y-axis, we have the error. And we see three lines. They represent three different machine learning approaches. The one in the red is the steepest. It has the smallest time constant. It will converge the fastest, and it has the highest learning rate of 1.0. In the blue, we see the most shallow or the more shallow approach. It will converge slower, it'll have a larger time constant, and consequently has a smaller learning rate of 0.5. And in the middle, we see the yellow line, whose steepness changes, the time constant seems to vary, and that's because it employs the adaptive learning rate. Its learning rate is constantly changing from iteration to iteration. Now, to understand why the yellow line behaves the way it does, we need to take a look at the bottom graph. For this one, the x-axis still represents iteration number, but the y-axis may represent a different value depending on which line we're looking at. So let's begin by taking a look at the green line, the delta loss. This tells us how the error, how the loss changes with a given update. For iterations 0 through 5, we see that the green line is negative, so the loss, the error, is decreasing from one iteration to the next. This is generally considered to be a good thing and coincides with case number 1. Between iterations 5 and 10, we see that the green line is positive, so the error is increasing with each iteration. This is generally considered to be less good and coincides with case number 2. Now, consequently, for iterations 0 through 5, we see the learning rate increase. And for iterations 5 through 10, we see the learning rate decrease. Now, what effect does this have on the yellow line? When the learning rate is increasing, we see that the yellow line becomes more steep, it approaches convergence more quickly, it seems to have a smaller time constant, and it takes on the behavior of an approach with a larger learning rate. For iterations 5 through 10, when the learning rate is decreasing, we see that the approach becomes more shallow, it seems to have a higher time constant, and overall, it takes on the behavior of an approach with a smaller learning rate. We can further explain this concept using an example of someone driving their car down the road. Let's say you're driving your car down the road, it's a straightaway, and as such, you have pretty reliable knowledge of the path that lies ahead of you. Consequently, there's a relatively small chance of your car exhibiting unstable behavior, for example, running off the road. Therefore, you feel comfortable increasing your speed or quote-unquote increasing the learning rate. Then you come up on a blind curve. At that point, you have much less reliable information of the path that lies ahead of you. Consequently, there's a relatively higher chance of your car exhibiting unstable behavior, and therefore you'll feel much less comfortable driving fast, and you'll be motivated to decrease your speed or quote-unquote decrease the learning rate. Next, I wanted to discuss some popular adaptive learning rate strategies supported by PyTorch. One is A-to-grad. This reduces the learning rate for weights that exhibit rapid changes and increases for the opposite. This helps to normalize machine learning emphasis between weights that vary in frequency or scale. There's also RMS-prop, which applies a method similar to A-to-grad. However, it employs a moving average of recent gradient magnitudes to smooth the adaptive learning rates and prevent any value from becoming too small. I think the last few slides did a good job discussing the advantages of an adaptive learning rate. However, we will spend 1 minute reviewing those here. One advantage is potentially faster convergence. The method may improve training speed by increasing the learning rate to emphasize the most effective updates, those that best represent the path ahead, going back to our car analogy. An adaptive learning rate may reduce the time spent in gently and constantly sloped regions of the error surface or error manifold. Another advantage is improved stability. The method may improve stability by decreasing the learning rate and speed when updates are less effective. Let's say, for example, the algorithm is approaching the edge of a region of attraction associated with a minima. An adaptive learning rate reduces the probability that the algorithm overshoots the minimum in steeply sloped and highly nonlinear regions. Another advantage is the reduced need for manual tuning of the learning rate. The method somewhat automates this process and reduces the need for us to manually tune the hyperparameters. A fourth advantage is that the adaptive learning rate performs well for sparse and noisy training data. The method may adjust the learning rate to emphasize the effect of cleaner, more reliable data samples and de-emphasize others that exhibit more significant noise. In this script, the stochastic gradient descent optimizer was configured with 3 key hyperparameters: the learning rate, which we've discussed at length, as well as momentum and weight decay. Here we see the command from our Python script that defined the optimizer, which we call myOptimizer. It's an instance of the pytorch.optimizer.sgd, or stochastic gradient descent class. We fed to it the model whose parameters it will update. We also fed to it a learning rate value, a momentum value, and a weight decay value. So what significance do the latter two have? Weight decay penalizes parameters with large values, or large weights, by adding a normalization term to the error, reducing the effect of near future updates on those large parameters and the probability of overfitting. Gradient descent with momentum, the third relevant hyperparameter from the previous slide, remembers the update associated with each iteration and determines the next update as a linear combination of the new gradient information and the previous update value. It's sort of like a bowling ball rolling downhill. Its trajectory may be nudged in a different direction by, let's say, kicking it to the side, but not instantaneously and completely redefined. There are 2 relevant implementations that we'll discuss. One is classical momentum that behaves like quote-unquote real-world momentum. Note that in the next module, we will provide a mathematical description. The second relevant implementation is the Nesterov accelerated momentum, which anticipates future positions to improve stability and prevent overshooting. Again, another topic we'll discuss in depth as part of the next module. Essentially, gradient descent with momentum prevents individual updates, which are reflective of smaller scale topologies, small bumps in our manifold, from derailing a machine learning algorithm that's exhibiting a continued, successful, and effective descent path. In conclusion, this module taught us to build a machine learning-based image recognition algorithm from scratch using PyTorch, covering key topics such as advanced PyTorch module design, adaptive learning rates, as well as momentum and weight decay. Watch the next module to learn more about optimization and gradient descent.